Welcome to this most excellent presentation doing what I call intermediate SQL. We assume that you know basic select, from, and where conditions, and we are going to cover several elements beyond that. So I'm excited and I hope it's very useful. Here we are going to show the three tables that we use for many of our queries, and in fact we use the same three tables in several other videos. The first one is company information, and it has a ticker symbol, a company name, an industry, a phone number. Address needs brackets around it because it's a reserved word. It would show up as a different color. Probably not in the create statements does it cause a problem, but it does when we do queries. City, state, again it's a reserved word, zip code, and country. Next is the calendar table, and it has an actual date, a month name that's reserved, day number, year number, day of week, and day type. Now day of week is going to have values Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Anything else is disallowed. Day type, there are three types of days: business, weekend, and holiday. So that will have one row for every day of the year from January 1st, 1900 through December 31st, 2050. The third table is stock data, and it includes a price ID, and that is our primary key. It's also automatically generated, known to be identity here. So the first assigned value will be a 1, and it increments by 1. Then we have ticker symbol, and we'll relate that back to company information table. Then industry, trade date, which is connected to the calendar table. Open price, high, low, close, and volume. Now notice that our primary key again is price ID, and it's going to have a clustered index. We also have a relationship, as I mentioned, to the calendar table on trade date, and we have a reference to company information on ticker symbol. Let's look at the data. Here's stock data. I know it's tiny, but we have a price ID, a ticker symbol, an industry, a date, an open, high, low, close, and volume. And that's a row for every day for every ticker symbol for about 20 years. Here's company information, and we have one row for each company. Here's Apple, the name, the industry, the phone number, and so forth. So there's 100 rows in this table. And lastly, here's the calendar table, and there's one row in here for every day from January 1st, 1900 to December 31st, 2050. And it's going to be useful when we do some date time type of queries. Here is query 1 in the intermediate SQL portion. This first query, we are going to count the number of price IDs in the entire table. There's no where clause here, and there's no group by. So we will count all of the price IDs. Now normally when we say that, that means that we're counting the non-null values for that column. And in fact, that's what it does. But price ID is a primary key, so by definition there can't be any null values. So we hit execute, and we see that the number of rows in the table right now is 427,405. Here is query number 2, and it is pretty similar to the first one, except this time we're doing a count star. Count star counts the number of rows, whereas count attribute counts the number of non-null values. So let's highlight this, execute it, scroll up our answer, and it has the same number as we did last time, but I wanted to show you a count star. Here is an aggregate called min. So min is going to be applied to the ST close column. So we want the smallest value in that entire column in this case. So let's execute it and scroll up our answer. And we see a tiny, tiny value. So somewhere there was a closing price of 6 cents. The fourth query here is a max. So if you have a min, I suppose you must have a max. So let's highlight this and execute it. Scroll up our answer. So we are looking for the largest closing price in the entire data set. Because we don't have a group by, we don't have a where, it's just max for that entire column. And the largest closing price then is $2,307 and almost 68 cents. Query number 5 then follows, and it is an average. In this case, it is going to be an average of the entire column. If it was with a group by, then we would be calculating averages per group. Let's highlight this query, execute it, and see that the average for all 427,000 rows is $52.28. Finally, query 6 is sum. Sum means to give the entire total. So we are going to add up all the closing prices in this query. So let's highlight it, execute it, look at the answer, and it is a very large number, 22,346,707. So that gives us a sum total of the entire column. So getting an aggregate on a column by itself is okay, but it's of limited use. Here is our first query where we're seeing an aggregate, in this case count, and we're going to count the number of ticker symbols for each industry from the company information table. So the company information table has 100 rows, and we're going to see how many ticker symbols or how many different companies in each industry. Let's execute it. Then let's look at the answer. And we didn't do an order by, so we're not seeing it in ticker symbol order. Yeah, I think it's in industry order. Query 8 is pretty much the same query as 7, except we've introduced the having clause. So again, we have industry, and we have count ticker symbols, and we're grouping on industry. But this time, with the having clause, we're looking only for those times where an industry has more than 20 ticker symbols in it. So having is a condition, and it's similar to where. Where is a set of conditions on rows. Having is a set of conditions on groups. So let's highlight it, run it, and we'll see that there is only one industry with more than 20 ticker symbols, and that is tech. I wanted to show query 9 and 10 together. Query 9 is counting ticker symbols from stock data. That's going to count every row that has a ticker symbol in it. So that answer will be about 427,000. Query 10 is very similar, but it's count distinct ticker symbol. Students sometimes forget where to put the distinct, or why distinct inside of a count is kind of unique. But let's run these two queries, execute, and see that the first one is 427,405 and the second one is 100. Again, that is because one of them was counting all rows that had a ticker symbol in it, whereas the other row was counting only unique values. This is our first query that includes a join. So we have ticker symbol, which comes from both tables of stock data, company information. We have trade date and ST close, both which come from stock data. And we have phone number and city, which come from company information. So we need to join these two tables in order to get them both in our answer. Here we have stock data as SD, and SD is what's known as an alias. And so in place of a table name where I need a table name, I can put its alias. Then I have CI, which is an alias for company information. Here is where I join the two tables and specify the common column. And I have to preface both of the columns with either an alias or a table name, which I've done here. Lastly, notice right here we put the alias in front of ticker symbol. And we have to specify that or we'll get an ambiguous column name error. And so in this case it didn't matter whether it was SD or CI. So let's run this query. And we'll scroll up the answer and notice that we show ticker symbol, trade date, close, phone number, city, and the answer to any query, the results are a table. So let's see something besides just this one, maybe Cleveland here. So that's the first join that we did, and we get a nice answer. And turns out that joins are the most common construct in all of SQL. This query is very similar to the last one, and the only difference is we're introducing a left join. This is a one-sided join, and what it means is it will say return all rows from stock data regardless of whether or not there's a match with company information. Now in this case I did a simple one. I have a little bit more advanced example here in a minute, but we want to return all stock data and matching company information. Well, on this query there's a parent-child relationship that company information is a parent and stock data is a child. So it turns out that every row in stock data matches and has to match to a ticker symbol or a row in company information. Let's execute this. And we will see virtually the same answer. It is the same answer as last time, but I wanted to start introducing joins that are something other than just a join. Those are also known as an inner join. So when we get done, we hope to define an inner join, a left join, a right join, a full join, and a cross join. Query 13 is quite similar to query 12, except this time we have a right join. Right join means that we want to return everything in the right table and matches from the left table. So the reason it's called a right join is the table on the right is the one where everything's returned. If it said left join, then it's everything here. So it's the same query, and in this case it's going to give us the same results, but it's nice to see how to do it. I execute it, I'll get the same results. When you do one-sided joins, a lot of times it's more instructive if they don't have parent-child relationships to be able to show people. And in fact, we do that here in just a few more queries. Query 14 is our first example of a full join. And a full join means give me all rows in stock data, give me all rows in company information, but when there's a match, show it. And a match means where ticker symbol equals ticker symbol. Now interestingly, if stock data had a row that didn't match to one in company information, then the attributes on the company information side, phone number and city, those would be null. Also, if there was a row in company information that didn't have a match in stock data, then the stock data attributes would be null. So when we get into some more advanced queries, that's kind of nice to know because we can test for those nulls and in fact see if there was a match. So let's run this query. and we'll see that we're getting the same answer every time, mostly because we have a parent-child relationship there. So that's a full join. This query is going to illustrate a cross join, and a cross join isn't like any of the joins we've done so far. It's not an inner join, a left join, a right join, or a full join, mainly because we can combine two tables that have nothing in common. And in kind of the distant future, we'll do some pretty hard examples that make a lot of use of cross joins. So a cross join is also known as a Cartesian product, which means that for each row in the first table, it's combined with every row in the second table. And I mentioned that there need not be a common column between the two tables. So we're going to introduce two new tables, and they are toys and colors. It's kind of fun to do because they don't have a common column, and because it's really easy to see what the combination looked like. Let's execute this, and let's go insert some data. So we're going to have blue, brown, purple, green, yellow, and we'll execute that part. Let's start doing the toys. We're going to have a train, a ball, a yo-yo, jacks, a doll, wooden horse, truck, and Lincoln logs. Let's execute that. Now, let's do a cross join. And my students, a lot of times I'll tell them, when you do a Cartesian product between two tables, the result is going to be the number of rows in one table multiplied by the others. And the number of columns is going to be the number of columns in the first table added to the number of columns in the second. So my mnemonic for my students is you times the tuples and add the attributes. So let's go ahead, run our query, and scroll the answer. And notice that we have every toy in the color of blue. So we have a blue train, ball, yo-yo, jacks, doll. Let's see, wooden horse, truck, Lincoln logs. And then we go to brown. So we have each toy with every color. And this is a simple example, but understanding how a cross join works is going to make it so that our future queries are so much more powerful. This query, query number 16, is taking a different direction than the several joins that we've just done. This one is a subquery, and it's kind of a cool subquery because it's the kind of subquery that has to be in a subquery. It can't be done in a join or another way. So this question would be, the question that would elicit this query is, please return the ticker symbol, the trade date, the closing price of the stock, and only do so for those closing prices that are above the average. So I like to tell my students that these work best if you understand that they work from inside out. So if we run just this inner portion of the query, and let's look at the answer, then we see that it's $52.28, almost 28.5 cents. So this inner query runs and calculates $52.28. Then it takes that scalar value of $52.28 and inserts it into this where clause. So then the query reads, return ticker symbol, trade date, closing price from stock data where close is greater than $52.28. Now, if you were unfamiliar with SQL, you might say, why don't I just put this select average right here? In fact, why don't I just put where ST close is greater than average ST close? Well, there are good reasons for that. One, you're taking an aggregate and then comparing it to a row value, and that's not allowed. It doesn't really even make sense. So you have a rule that says you can't have an aggregate in a where clause. Well, the way around it is to put an aggregate in a subquery and let the subquery feed to the outer query. So let's run the whole query, and notice that we're getting only those values of the closing price more than that $52 value, and you see that in fact all of those satisfy the condition. So it's one of my favorite queries to show students because it's a subquery that has to be a subquery, and the subquery also contains an aggregate. Here is a nice query again that shows the subquery. Now the subquery is going to find the ticker symbol for companies that exist in the states of California, Washington, and Texas. So any ticker symbol whose home company is in one of these states is collected, and then it's returned to the outer query. So if I just run the select portion here at the bottom, I can see all the ticker symbols that are in those states. In fact, I'll go all the way to the bottom here. So we had 33 of our ticker symbols that came from those states. Now if I run the rest of the query, it gives me the ticker symbol, trade date, and closing price. Now there are a couple of items here. I really wanted to show an in right here, so you can connect your subquery with an in, and I wanted to show an in as well right here. Another thing I always tell my students here is this ticker symbol here in the outer query, in the where clause, has to be the same attribute as what's in the inner query select. So we always have to talk about the same thing. Even if, like on the previous query, we have a scalar value, it has to be meaning the same thing as what's in the where clause. So again, one of my favorite queries, it's well known that you just could have said where ticker symbol in this where clause, but I wanted to show an easy subquery connected with an in. Here is a subquery that you don't see very often in beginning books, and that's a subquery in the outer select. So the question would be, please list the maximum closing price for Ford. Please list the maximum closing price for Microsoft. And these will be in two different columns. So if I want these two largest prices in two separate columns, I did a subquery here, and then I did a subquery here, and I will execute it. Execute the whole thing there, and I'll scroll up, and notice we see the largest value for Ford, the stock, and then the largest one for Microsoft. So again, it's atypical in beginning books to see subqueries in the select clause, but that's how you can get a specific value for a column, and even if you have multiple columns. Query 19 is a lot of fun here, and it's a little bit complicated, and most of my students, hardly any of them, have ever seen it. So the question that would elicit this answer is, please give me the ticker symbol and the average closing price for the stock that has the largest average closing price. Now what my students really want to do is put in front of average here, maybe max of average. Except that you can't stack aggregates. And so we're going to be a little bit clever here, and we're going to have a subquery that calculates, again, the average closing price. So I might execute that, and that's going to give me the average closing price for every ticker symbol. It's not going to list those. Let's see if I can make this appear. It's not going to list the ticker symbol, but it'll list the average closing prices. So let's scroll that back down. Now, the key to this entire query is this having clause. And what we're going to say is having the average closing price, because you can put an aggregate in a having clause. We're saying having an average closing price greater than or equal to all values in the subquery. So most of my students have never seen this all operator. The inner query then calculates a list of average closing price, one for every stock, and then the outer condition is give me the one that is greater than or equal to everything in the list. Well, only the largest average price will satisfy this having condition. So it will return only one. There's not a tie in this case. But so let's highlight that and execute it. And in fact, it's Google. And for this time period, it's $505, almost 11 cents. So it's, again, kind of a cool query. It's fun because most of my students have never seen it. Even the kind of the ninjas in my class have never seen it. I suppose if I showed an all operator, that I need to also show an any operator. Again, it's one that my students generally haven't seen. So this inner subquery, we're going to look for trade dates where the closing price was greater than $1,000. And it turns out that there are a lot of days, I think a lot of them are Google in fact, where the closing price was more than $1,000. So we are going to have that feed into the outer query. The outer query wants to show attributes from the calendar table. Here's the calendar table. And essentially what we're saying is show an actual date, a month name, a year number where there were any closing prices greater than $1,000. So I highlight it, execute it, and now I get to see those attributes from calendar, actual date, month name, and year number for those dates where the closing price was greater than $1,000. Again, the any operator is rarely seen, but when you need it, it's really cool. Query 21 will be the last query in this video. And again, it's one that a lot of people don't see. So this inner query is going to give me a count of the number of rows essentially in stock data. I in fact have a correlated subquery. What that means is company information is in this from clause, stock data is in this from clause, but we join company information to stock data here in the inner portion of the query. So correlated subqueries are harder to write and they run a lot slower. However, for certain classes of problems, they're totally awesome. In this query then, I'm going to show all rows for companies that have more than 3,650 rows. Again, another thing my students rarely see is a number like this on the left side of the operator. So it's an unusual query from basic and beginner books, but this one is going to show companies that have more than 3,650 trading days. I scroll that up, and I don't have all 100 stocks, but I have 73 of them. So in my data set, I have at least I have 73 stocks that have traded for more than 3,650 days.